ההורים שלך לא באים.
לא.
So, actually, instead of what I have talking the previous time, we will begin it again to talk the study. So, as we said, the group will be called super divisible. For any word of n variables, and for any element in the group, there are elements h1, hn in the group such that f of h1, hn is equal to g. It obviously generalizes the notion of a divisible group. Now, so the claim is that we can embed every countable group into a finitely generated super divisible group. So let me state it. Theorem every countable group can be embedded into a finitely generated super divisible group. Super divisible. So, in order to prove this, we will do some preliminary work. This is in the following way.
Didn't you do it last time?
Huh?
Didn't you do it last time?
Yes, but erroneously.
What?
With errors.
Really?
No, actually not with errors, I just did the work. So let me explain it this time. So, what we have to do? First, if we would not have this requirement that the group must be finitely generated, this will be quite easy. Namely, we can do the following thing. We can take all the possible words in n variables for each n, actually for different f's we take different variables, and then we can do the following. Actually, we have to distinguish between two cases. This element G, what we consider in the group, it could be of a finite order and it could be of an infinite order. And actually, we need to do different things when if G is of infinite order, second, G is of some order n.
But if the group is torsion free, what you did last time was okay. Yes?
No, of course not.
No?
No. And not it wasn't okay, I just didn't it. Because I only said the first step of it. Now you will see that actually it must be much more. So, what can we do? We can consider a group, say, HF with the elements x1, f, x and f, here where this n may depend on f. Now, and then in this group, we have a cyclic subgroup generated by the word f of x1, f, x and f. And n may depend on f, of course. Now, so let me call this subgroup CF. Then we can take the amalgamated free subgroup of all these groups with this CF being equal to each of these in the case when this group is an infinite cyclic.
What is the x1f? Just
These are different variables because
Okay.
each of these groups needs different variables.
Mhm.
And n is also different. N might define n might
Yeah,
define
yeah.
n doesn't matter. So we have here a free amalgamated product amalgamated with a common cyclic sum. And the same we can do separately when we take here and of H, F, M. So we actually take the similar group depending on x1, f, x, and f, and we divide it by the element normal sum generated by f of x1, f, x, and f to the power n. That means the normal subgroup divided it. Because this is one related subgroup, so this procedure is correct. Because this is a single related. This is by a normal subgroup generated by a single element. So and we can do the same thing here when we just take similarly the free amalgamated product of all these groups.
And what is the common cyclic subgroup? It is element f,
This is here generated by f, of course.
It's f. Yeah.
And here we have generated the same thing, but this will be generated by f divided by f to the power m, so this will be the common subgroup will be a finite cyclic or group of order. But the same idea. And then if we take our group G, and then we wish that all these equations will be solvable here, so it depends on whether G is on an infinite order or on a finite order. If it is on infinite order, then we take just the amalgamated product when G is equal to a corresponding f for all of this, running over all this, and then we have added all these solutions equations. And if it is of the m, then we take G with G is equal to f to the power n. And also we take the analogous configuration. Okay. So, but then we need to repeat this for all the elements in these groups, and then we have a increasing sequence, and the if we take the union of the increasing sequence, so of course this group will be super divisible, it will be countable, but no chances to be finally generated. So the whole question is how to get a finally generated. So, and this actually we will now. So I'm starting with a free group. Now I could take with two generators maybe on 4 generators. I will take 2 generators and there will be no problem because we will need that our votes will start by correct letters in order to avoid some cancellation problems, but I will just neglect it because it will easily done. So, what we do? We take a quotient of this group one with G embedded in this quotient. Now, 2 with countably many copies of let me call this group K0 and let me call this Km of groups K0 and Km of M actually need of B or Z or Z of 1. Okay. Inside this group. Each of them needs infinite, countably many copies.
Do you want a G-free product with infinitely many copies? You can always make sure of that.
No.
You don't care?
I know. Actually, it will be independent embeddings. So let me explain how I'm doing it.
Well, you can always embed a free product. Still countable.
I can, but I don't want. Because you will see now that it is more economical to do in a different way, and they should actually many ways that are roughly equivalent. So what we're doing when we take this group G, so for every element G, we have a word, I called it x to the power alpha of G, y x to the power alpha of G plus 1, y, etc., x to the power beta of G minus 1. So let me notice, earlier I did not the W, maybe I will need W for another. So let's call it U of alpha of G beta of G. So we actually embed G in the way that this goes to this element for every element of G. Now, and then we embed, and then we impose relations that just imitate the multiplication table of G. It means if in the group G we have G1 times G2 equal G3, so we impose a relation U alpha of G1 beta of G1 times U alpha of G2 beta of G2 equals to U alpha of G3 B beta of G3 for all G1, G2 in the group and G3 their product. Okay. Then we do the same thing independently for countably many copies of K0 and countably many copies of Kn for every integer. So now we obtain a group F over N is with these embeddings. Now it is clear that the group F over N is a small cancellation group. Of course, not finitely generated. Of course, not finitely presented.
Small constellation, not in the standard sense.
So let me see. What I said is that we extend the definition of small constellation in the way I said that if we have two relators such that so their product is also in the liquids of the relator, then we actually, then this is not considered to be a small piece. What we do here, actually, we take the list of generators for all the situations when we have G1 prime G prime GS prime equal to 1 for any S. So we take all these relators in our list. I mean U for alpha G1 prime beta G1 prime, U alpha of G prime S beta G prime S. All these will be the relators of this group.
Yeah, but this is rather what you're claiming. Okay, you claimed it also last time that practically every finitely generated group or every countable group even can be embedded inside the finitely generated group, which is small constellation in some sense.
No, but this is actually only the starting point of our work.
No, okay.
So far we achieve nothing.
What did you?
No, because we need the roots of all the solutions.
No. But you did achieve that you embedded a group inside the group. Inside the group, which is some sort of small constellation.
Yes, okay. This was done, but now I'm doing this one for the original group G and two for all of these groups. And each of them is embedded differently, counting them many times. There is no problem with this because we take all these intervals to be disjoint. And this is, of course, no problem with it. Even if we accept the countable version of the axiom of choice. But, okay, so we have this group. Now, when we have this group, and this is a small cancellation in this sense, because then every true small piece actually must have no more than one instance of y. Because otherwise this is in fixed limit. Because all these powers of x are different, because all these intervals are disjoint, So if we have two instances of a letter Y appearing in the small piece, so it will already fixes the place in it. Okay, fine. Now, by the way, let me now define in this group the notion of, let me take lambda something like 2/3. And let me define lambda semi-canonical word in this group. What I mean by lambda semi-canonical words in F over. Okay. Indeed, we define it in the following way. First, we look on the chart of a board. If we have an arbitrary board, then we look on its chart. In which sense we consider the chart of it? Only when we have the words of this type, x alpha, y, x alpha plus 1, etc., x beta minus 1. So all their inverses, because we're now in a group not in a ring, and then we consider all the instances that we have such words, but when they are part of those intervals specified in all these embeddings we used in this photo. We specified actually a countable number of intervals, and when we see the words of such type or their inverses subgroup, then we mark them in the chart of this group.
Yeah, well, why can't you just impose now the relations that says that, as you did before, now impose the relations, it will not work?
No. Yes, what you will see. So we look on this, let us call it standard words. So actually, what we are interested, so there may be only a part of the standard word. Maybe it middle, or maybe at beginning, or maybe at end, or maybe it could be the whole standard word, whatever. According to this sub-segment that we took for these embeddings. Now, let me say the following. If we have in some place two standard words that correspond to the same subgroup, because we took countably many different groups. Assume we have two standard segments that correspond to the same group. So this corresponds to some element G1. This corresponds to some other element, maybe some element G2, belonging to the same group G over some of the groups. Then their product G1, G2 is equal to some G3 in the same group. Then we can just substitute this by the segment that corresponds to this element G3. So we reduce all such instances whenever we encounter them. So we may assume that a word representing element in the group does not have two full intervals. So what may happen is that we may have one interval, and then this is one, and then the beginning of the next one and the end of the previous. This is the full interval. This is just the initial part. And this is the final part of this element. If the signs are opposite, then we have the inverse of initial on this side and the end of the final of the etc. Now, because if it would be in full, then we can reduce it. So what we can do now, if this is more than lambda of this segment, then we actually can then add this one. We just take this product, which will be another word. Let me take it by just another color. And then we have this part of it. So actually, this word is equal to this one, this a full segment, and then the opposite of this. And the same could be done here. So when we say the word is semi-canonical, then these both parts are less or equal of lambda of a segment. So we allow one segment in the standard way as it is, and on its side maybe no more than lambda part of one of it on the other side. So one can easily see that every element could be presented in this way, and this will be called the lambda semi-canonical words. Actually, we call them actually lambda semi-canonical words of rank 0. This is our definition of lambda semi-canonical words of rank 0. Okay. Now, and of course, every element may have different presentations by lambda semi-canonical words, but we don't care. We just know that it is not unique. Now, the next point is, let me enumerate all the elements of the group G over N. Let us enumerate all the elements of G over N. So we have a sequence of elements G1, G2, etc., exhausting all this group. Now we proceed just inductively by the by N, but we actually work with each of these elements. So let us start with G1. G1 is an element of this group G over N. It might be of an infinite order, it might be of some finite order N. So, what we do? We add just one relation. The relation is that G1 is equal to, actually we look not at the G1, but at the U of alpha of G1, beta of G1. This is the word representing this element in this group. We take it equal to U of some alpha of some K1 beta of K1, where this K1 is just the generator of the amalgamated subgroup. K1 is a generator of the amalgamated subgroup. It could be K or K1 because it has many copies. So we just take some particular copy of this group.
This is not related to the semi-canonical words at all.
Not at all. Not at all. because this
We've
was
done it before.
exactly because this was the semi-canonical word in rank 0. Now we just impose one new relation. What will it mean? That now this, so for this element, now here the group, the image of this group will provide all the solutions of all these equations, but only for this element. And it depends whether it is of finite or infinite order, and then the corresponding group is already embedded in f over n, and then we just add this. Now, of course, let me call this element W1. I mean, not this element, but a word, just W1, let W1 be a lambda semi-canonical word around 0, representing G1. G1 is element of this group, and we take a particular, we fix some lambda semi-canonical word, G belongs to G over G1. And we take a particular lambda semi-canonical word that presents it.
This will change. Why? For element in the group, this will change. I mean, this relation will change the semi-canonical. Why can't you take?
No, why now we impose a new relation?
Yes, right.
So now when we are choosing, so this is something fixed word.
Yes.
No, excuse me, not this one. Just, sorry, W. Because when, excuse me, oh, very important. This is a enumeration of the group G over N. No, F over N, sorry, F over N, I apologize. We started with a free group. Group G is embedded into F over N. It is not, this is an enumeration of our group F over P. So, we don't know what is actually the particular form of this element. It is just some lambda semi-canonical word. But of course, we can ensure that taking this in I big enough, that this group and all the elements on the segments which present element here are much longer than the length of W1. This is important. The length of W1 is much less than U of UK. I beta of ky, I mean for all k1 run in this image of this group k, k0 or km I. So because for every group we have its own sequence of these intervals, and then we can just provide that all of them are much more lengthy than this our word W. So what we do now, we take also all, so actually we also add, so we view this element as a substitute of this. So when we have all these relations in the group, say k0, km, so then we take this element as well as a substitute of this element. I mean, W1 is a substitution of K1. So if we had a relation, for example, this particular K1 with some K2 was equal to K3, or in general we may have, so we take now this W1, K2, and K3. And in general, when we have a sequence of elements, the product is equal to K1, K2, Ks is equal to 1. In this group, Ki, I mean, it will be 0 or then we can take now W1, K2, Ks equal to 1. Just because now W1 is taken to be equal to this element. Now, why this group also, now, this group will satisfy the small cancellation conditions because this W1 is much smaller than all these elements. Because this is long segment and this word, whatever its structure, is much shorter than each of them. Okay. Why? Because then, when we have to look at it, we have two relators of the same type. Now, it might be that this word K1 is this word W1 may be common here, or it might be that this W1 appears in some other place, or it could be even in several places, you see, but we have all of them long one, and one W is a short of them. And then when we have, if this is a common part such this product is again in the list of the relators, then we know that it is that still this is not a small piece. Whether it is a small piece, when it is either of this only one common word B, or something that are common with W1 and one of these segments. In any case, even if it is with the whole W, it will be a very small part of all the rest of the relators. Therefore, still we have our small cancellation condition. Just because we consider that the length of W1 is very small, and all of them are very big with respect to it. So this group also will satisfy the small cancellation condition. But now we have to take what will be the semi-canonical form in
what type? You had only relation inside this K, or you take?
Yes, just because I have one element for which I need to have all the roots of all these equations. But inside this group, I already have a standard element that inside this group is already present all the solutions of all the equations, because this is a part of some group K, and this is just a common part between the amalgamated cyclic subgroups. It contains inside this quotient group all the roots. And in the way that we still have the small cancellation, because they will have taken the lengths of the segments much bigger than our W1. But now the question is, what will be the lambda semi-canonical word in rank 1?
Yeah, but maybe W1 itself participate now in another relation. Yeah, that could be.
Just a moment. Let me just make a break. But W1, we don't know anything of it. The only thing we know about it, it is short. Of course, it could be of any form. It could be any lambda semi-canonical word in rank 0. Particularly, it could be just, you cannot say nothing. He comes as it is.
No, but the fact that W1 appears here means that every part of it is now considered as a piece. If it appears in another relation somewhere else, it's short in this relation. This is true.
Yeah.
But this W1, you don't want it to be a piece, right? There could be parts of it.
No, I can't say that. But I'm only interested that the rest of the relation.
No, these relations, but you have relations from before, from level 0.
It doesn't matter.
Why?
Because all the words we consider as are semi-canonical in rank in rank 0. So no of these relations can have more than
Lambda.
just for the structure described here, a standard piece and two pieces with of length no more than lambda of it.
Right, but lambda times a relation is something rather big.
Isn't it?
2/3 times a relation
Yes.
is rather big when you consider level 0. You don't care?
I don't. Because all these segments are disjoint.
Yes.
So they have no chance to interact with the words in this group of K.
The groups of K, yes, that's true. Oh, okay, you say that. Oh, so you're going to use two things at the same time, right? One is you use this two generals, one constellation. One is gluing relations, and the other is you're braiding the relations as well.
Yes.
Both of them at once.
Yes. Now, then I just is of the camera. I'm going to define now the semi-canonical word in rank 1.
Yes.
Which I will define it, but then it means that instead of these standard segments for the group K, one of them might be W1 here in the middle plus minus 1, or even any, or even it could be part of this or part of this, but not, yes, but then the rest of them should be sub-words of the standard segments. And this particular double could take, because we replace the standard segment by a short double.
Who was the first who constructed this group?
What group?
No, superdivisible group.
This is a new definition.
Sorry?
This is a new definition.
Superdivisible, I understand.
Yeah, can there be
So divisible group was constructed
By Shansky, somebody in office 2 years.
I see. And now it's a generalization.
In a sense, yes.
Yeah, one can do even this super divisible, which is also a torsion group.
This I'm saying, because I have to accommodate the two cases. With some of these group elements might be of finite order.
No. But I wanted the whole. You construct. Okay, suppose you construct now a super divisible group.
Yeah.
But one, and then you even prove that every countable group embeds in such a group.
Yes.
But you can ask. It's not much more. Just to ask that to construct a super divisible group, which is by itself torsion group. Every element has a. Like Burns a group like this. What?
Of course, you can do it.
Can do it, yeah.
But it is, and you might even, if the original group had only
No, you don't
token
stop.
to bounded exponent,
Then what?
if the original group embedded in this had torsion of bounded exponent,
Yeah.
for example, if it was a torsion to the bounded exponent,
Yeah.
then you can care that the output group will also be a bounded exponent. Big bounded exponent.
Big one is what?
But it incorporates, yes,
And the group will be embedded.
yes, incorporates Bernstein.
It's Bernstein plus this.
But it, of course, one have to care about. Well, we need to travel with all the travel with the Bernstein, but not more than this. Hmm?
You want to fix time. Okay.
Now is a break, but you tell me when I finish the break.
Yeah, okay.
Switch them, this convenient for you, maybe. Now,
This moment.
doctors issues, maybe.
Sunday. Now we don't have class.
Okay, so, but when they are coming to university? Theoretical. Why it's no classes?
Is that work there?
They just prefer